8-4, continuing with infinite geometric series. Alright, infinite geometric series, we're adding infinite amount of numbers as long as they're geometric, and we're going to look to see when is it possible to add them, when is it impossible to add them. I am going to go ahead and start with number 1. We're adding 1/4 to 1/6 to 1/9 to 2/27 to 481. Alright, the partial sum that we're doing right now is the first one. The first time we only have one term to add, which is 1/4. 1/4 is about 0.25. If we were to add the first two terms, we call it partial sum. So that means add the first two terms, the fourth plus the sixth, and that should add up to about 0.42. Partial sum number 3, that means you're adding the first three terms. Well, the first two add up to 0.42. I'm going to go ahead and add now 1/9 to that, and that will give me about 0.53. We're going to continue with this pattern till we add the first 5 partial sum. So if we add the first four terms, well, the first three terms add up to 0.43, and then I'm going to add an extra 2/27, and then 2/27 plus 0.53, and that's going to give you about 0.60. And the last partial sum that I want you to look at is adding the first 5 terms. Well, the first 4 added to 0.60, and if we were to add 481 to that, we would get a partial sum of 0.65. If we continue with this pattern, where do you think at some point this sum, infinite sum, is going to approach? And as you can see here, it's going to approach 0.65. Now what they're asking you to do, can you go ahead and graph them? Well, to graph it is no big deal. I want you to know on the x-axis we're counting n, on the y-axis we're asking for s of n. And so the n's, we're counting the first 5, 2, 3, 4, 5. On the y-coordinate, we're going to go very slow here. It's 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. We can go to 0.7 if we want to. So number 1 goes to 0.25, which is about right here. At 2, it goes to 0.42, and so that's going to be about right over here. And then at 3, it's going to go to 0.53, which is about right over here. So we have these points. And then at 4, it's going to go to 0.6. 0.6 is about right here. And then at 5, it's going to go to 0.65, which is about right there. As you can see, those dots, if you continue making them, it's never going to pass this line right over here at 0.65. It's going to get very close, but we'll never pass it. Continuing with number 2. Number 2 is exactly like number 1. You are going to add the partial sum of this particular series, and we're going to do it this way. We're going to go ahead and add the sum. So the first one, S1, it's only the first term. The second one, you add the 3 plus 3 over 5. And you can see that this one's going to be 3.6. The third one is going to be whatever you get on the previous one plus the next term. The next term is 3 over 25, which gives you about 3.72. And then the fourth one will be the first 3 added up plus the fourth term, which is 3 over 125. You see those sums? We call them the partial sum. And finally, we're going to do the fifth one. The fifth one is the first 4 added up to 374 plus the fifth term, which is 3 over 625, and that's going to give us 3.75. As you continue this pattern, you will find S of n is approaching 3.75. It will never cross it. I seriously want you to go ahead and graph it like we did on the previous one. And so this one here, you can count 1, 2, 3, 4, 5. And over here, I'm going to start at 3 because all my numbers is 3 to 375. And I'm going to count it all the way to 375. And as you can see, at 1, it goes to 3. At 2, it goes to 3.6, which is about right here. At 3, it goes to 372, which is about over here. At 4 is going to be 374. and at 5 is going to be 375. You can see those dots is going to approach 375, but they will never cross it. Number 3. For number 3, we're finding the infinite sum as n goes from 1 to infinity. And as soon as you see infinity here, I need you to check to see if r is between -1 and +1. R is 3/5, in this case right here. As long as r is between -1 and +1, and you only want to check that when you're doing infinite sum, you're going to find a1. And a1 is going to be when you plug in 1 into the formula, so that will give us a 6. The sum will be a1 over 1 minus r. This is the sum for infinite geometric series. So this will be 6 divided by 1 minus 3/5. And so that will give us 6 over 2/5 multiplied by the reciprocal, 6 times 5 over 2, which gives you, this cancel to 3, 3 times 5 is 15. Okay, number 4. Number 4, we have the infinite sum from 1 to infinity, 10 over 3 times 5 over 2 to the I minus 1. Well, the first thing we want to see, as long as it's infinite, we want to check to see if r is between -1 and +1. In this case, you see r is 5 over 2. 5 over 2 is 2.5. It's a lot bigger than 1. Therefore, we'll say the sum does not exist. Number 5, we will have this series 5 plus 5 over 3 plus 5 over 9 plus 5 over 27, and because it goes on infinitely, I wanted to check to see where r is the common ratio, and as long as r is bigger between -1 and +1, the sum does exist. And so now I found that r is 1/3, a1 is 5, so the formula will be 5 divided by 1 minus 1/3, which gives you 5 over 1 minus 1/3 is 2/3, multiplied by the reciprocal, so that's going to give you 5 times 3 over 2, which is 15 over 2. Number 6, we're adding these terms, 1/2 minus 1/4 plus 1/8 minus 1/16 plus ... meaning it's infinite. And as long as we know we're dealing with an infinite geometric, find r. And in this case, you can tell that r is equal to -1/2. It's a common ratio. a1 is 1/2. So the sum will be a1 over 1 minus r. And therefore will be 1/2 over 1 minus -1/2. And so that will give us 1/2 divided by 3/2. And if you multiply by the reciprocal, you will know that the sum is just simply 1/3. Okay, number 7. I want you to look at this one. The first swing, the pendulum travels 30 centimeter. On the second time, on the second swing, it traveled 30 times 75% of the previous distance. So we're just going to have to multiply it by 0.75. On the third swing, it traveled 30% of the previous term. Well, the previous distance traveled was this, so we're going to have to do 75% of it, which is multiplying by another 0.75. And so that will be 30 times 0.75 squared. And as you can see, every single time we count those swings, it's going to be 75% of the previous one. So the previous one was, this one is squared, 0.75 squared, and you're just going to have to multiply by another 75% of the previous distance. We can go on here to infinity. And so here is the idea. We're going to look and see if that pendulum kept on swinging. At the end, it's going to be an infinite series, a geometric series, where r is equal to 0.75, and on the first one, it traveled 30 centimeter. So the formula it tells you to do, s is equal to 30 divided by 1 minus 0.75, and so they'll give us 30 divided by 0.25. I want you to transfer the decimal to fraction and simplify it, and you will find that the sum is equal to 120 centimeter. Lastly, what we're going to do, we're going to take numbers that are in decimal and put them in fraction form. So if we start out with 0.12, 12, 12 repeating, well, this is pretty easy to make it as a ratio, as long as you take the 12 that's repeating digits and divide it by 99. And so reduce the ratio will give you 4 over 33. That is the same thing as 0.12 repeating. Those are rational numbers stated in two different forms. One form is a ratio, one form is decimal. Now let me give you a few examples here I want you to take notes on. If you have only one digit repeating, such as let's say 0.333, so that will be 3/9 because you only have one digit repeating, which is 1/3. Now let's say I have three digits repeating, let's say 1.25, 125, 125, and so on. And just because I have three digits repeating, you take the 125 and you divide it by 999. You must reduce your answer if it does. If it doesn't, that's fine. Those are your answers. Now what happens when the digit do not repeat? And so the digit do not repeat, I want you to take notes on these examples. And now we're going to try something very, very simple. We're going to say, okay, what if we have 0.2 and then it starts to repeat 3, 3, 3, 3. We're going to call this as a sum of bunch of numbers. And so the numbers, we add them as 0.2333 infinitely. And so now if you multiply this sum both sides by 100, so you'll end up with 100s is equal to 23.333 repeating. However, if you multiply both sides by 10, you will get 10s is equal to 2.333 repeating. What I want you to do now that we multiplied twice, we multiplied it by 100 to get the 23 out of the decimal, and then we multiply by 10 to get the 2 non-repeating digit in front of the decimal. I want you to subtract the 2. 100s minus 10s is 90s. 23 minus 2 is going to be 21. And so here if you divide both sides by 90, s is equal to 21 over 90. If you reduce it, it will be 7 over 30. You see now if you check on your calculator, 730 is the same thing as this decimal number repeating. Okay, the last example I'm going to give you right here, what if I have two digits that are non-repeating and then it starts to repeat? So this is what I want you to do. Call this one S. And so the sum of certain sequence that goes on infinitely, it's a 0.25 repeating 33333. I want you to multiply both sides by 1000 to get the first three digits out of the decimal place. So we will have 1000s is equal to 153.3 repeating. Now we want only the repeating digit to go in front of the decimal, so I'm going to multiply both sides of this equation by 100. So 100s is equal to 25.333 repeating. I want you to subtract those two equations, and when you subtract them, you get 900s is equal to 228. Divide both sides by 900, and you will find that the sum is equal to 228 divided by 900, it is divisible by 12, so it should reduce to 19 over 75.